We're told that there's a child on a merry-go-round and a parent is pushing on the merry-go-round. We're given the mass and radius of the merry-go-round are 100 kilogram and 1 meter. The strength of the parent's push is 250 newtons, and the child has a mass of 25 kilograms. If the parent wants to give the child as fun of a ride as possible, that is like saying, how must the parent push on the merry-go-round for the merry-go-round to gain as much spin as possible? So let's suppose the parent pushes on the merry-go-round, and I drew on the board that the merry-go-round is spinning in a counterclockwise direction. From this perspective, we're above the merry-go-round looking down on it. First, we could ask, if the parent wants to have the merry-go-round gain as much spin as possible, where on the merry-go-round would the parent push? The parent could choose to push the merry-go-round somewhere closer to the center or somewhere near the outer edge. Our intuition for how the world works tells us that the parent will probably want to push on the merry-go-round near the outer edge to get the merry-go-round spinning as much as possible. So let's say the parent chooses to push right here, 1 meter away from the center of the merry-go-round. We could also ask, in what direction will the parent push the merry-go-round? If the parent is to cause the merry-go-round to spin as much as possible, then the parent will probably want to push on the merry-go-round in a direction something like this. So we could say this is the force vector that the parent exerts on the merry-go-round. Now, let's think about what's going on. This is intuitively how we expect the universe to behave. If I want a merry-go-round to spin as much as possible, I would grip the outermost edge of the merry-go-round, and I would not pull in this direction or in this direction. I would push in this direction. Why is this? To see this, let's look at the equation for the torque on an object from a force. We could say torque is equal to Rf sine theta. In this equation, R is the distance between the center of rotation and the location where the force is applied. If I want torque to be as large as possible, then I will want R to be as large as possible. The parent could have chosen to push at any location on the merry-go-round. The parent could have chosen to push right here on the merry-go-round, halfway between the center and the edge. But if the parent wants the merry-go-round to spin as much as possible, then you will push on the edge, and that is essentially saying you are making R as big as possible. So we would say the torque on the merry-go-round is R, the distance between the center of rotation and the location where the force is applied. In this example, that is 1 meter. The strength of the force with which the parent pushes the merry-go-round is 250 newtons. So here is 250 newtons. And we have the sine of theta. In this equation, theta is the angle between the direction of the force vector and a line connecting the center of rotation to the location where the force is applied. As this picture is drawn on the board, the line between the center of rotation and the location where the force is applied is a horizontal line. And the direction of the force vector is towards the top of the board. So I would say this line and this vector are 90 degrees apart. So I would have sine of 90 degrees. And from what I know about the sine function could be anything between 0 and 1, depending on which angle you're considering. And I'm only considering angles between 0 and 180 degrees. So to make the sine function as big as possible, I want sine equal to 1. That implies my angle will be 90 degrees. And intuitively, this is the direction that the parent will push on the merry-go-round to maximize the amount of spin that the merry-go-round gains. So now I could put these numbers in a calculator, and I find the torque on the merry-go-round from the parent's push is 250 Newton meter. The units for torque are Newton meters. In part B of this problem, we are asked to find the angular acceleration of the merry-go-round with the child on it. To find the angular acceleration, we will use the rotational analog of Newton's second law, net torque, tau net equals I times alpha. In this equation, we only have one source of torque. That is the torque from the parent pushing on the merry-go-round. So tau net will be entirely the 250 Newton meters. The moment of inertia of the things that are spinning will be the moment of inertia of the merry-go-round plus the moment of inertia of the child on the merry-go-round. This question is kind of like the rotational equivalent of if I am pushing a shopping cart with a certain force and my dog is in the shopping cart, what is the acceleration of the shopping cart with my dog in it? We have two objects that are connected together. They are both accelerating together. And then there is the force I am exerting on them that causes them to accelerate. In this problem, we have two objects that are spinning together, the merry-go-round with the child on the merry-go-round. We have one source of torque, one source of something pushing on the merry-go-round that will give it an angular acceleration, and then we're going to try to find the angular acceleration. So what is the moment of inertia of the merry-go-round with the child on it? Well, if we place the child at the edge of the merry-go-round, so we'll place the child right here, we'll assume the child is very small, so the child could be approximated as a point particle. Then I could say the total moment of inertia of the merry-go-round with the child on it could be written as I total is equal to the moment of inertia of the merry-go-round plus the moment of inertia of the child. We said that we are assuming the child to be very small, so to a reasonable approximation, we could treat the child as a point particle. That means the moment of inertia of the child will be mr squared. How should we think about the moment of inertia of the merry-go-round? Pause the video, think about it. Think about what shape a merry-go-round might be similar to. The merry-go-round is going to be treated as being identical to a cylinder. To argue that claim, let's think about what a merry-go-round is. A merry-go-round is essentially a disc and it spins around its center and you ride on it. So this is an overhead view of a merry-go-round, but if I were to draw a view of a merry-go-round from perspective, then I would draw a disc that looks something like this. And the moment of inertia of a cylinder is given as 1/2 mr squared. So the moment of inertia for a cylinder, 1/2 mr squared. Think about what a cylinder is. And notice that the height of the cylinder is not contained in this equation. The moment of inertia cares about how far away from the center of rotation the atoms are in that cylinder. The moment of inertia does not care about how the atoms are distributed vertically in the cylinder. If the cylinder is of even and uniform composition, I could imagine I have a really tall cylinder, and then I have some atoms are pretty close to the center, some atoms are further away. And if I were to take this cylinder and scrunch it vertically so it becomes very thin, even though the atoms were all scrunched together vertically, there are still the same number of atoms 1/2 meter away. There are still the same number of atoms 0.75 meters away from the center of rotation. The distance from the central axis of the cylinder does not change for any of the atoms in the cylinder when I scrunch it down. So that is why a spinning disk has the same moment of inertia as a cylinder. And a merry-go-round is a reasonable approximation of a spinning disk. So I could say the merry-go-round will have a moment of inertia of 1/2 mr squared. So the moment of inertia of everything that is spinning in this problem, the merry-go-round plus the child, will be 1/2 mr squared. So 1/2, the mass of the merry-go-round is 100 kilogram. the radius of the merry-go-round is 1 meter, and then I square it, plus the moment of inertia of the child is the mass of the child times the distance from the center of rotation that the child is found at, which is 1 meter. So I have 1 meter squared here. And when I add these numbers together, I get the total moment of inertia. I total is equal to 75 kilogram meters squared. If I then plug this I into the rotational analog of Newton's second law, I would say tau net equals I alpha. There is only one source of torque, that is the torque from the parent pushing on the merry-go-round, so that would be 250. We found that in part A of this problem. The total moment of inertia is 75. The moment of inertia is 50 from the merry-go-round and 25 from the child, so I have 75. And then the angular acceleration of everything that is spinning. And when I put these numbers in a calculator, I find that the angular acceleration of the child and the merry-go-round is going to be 3.33 radians per second squared. At this point, we are done with part B of this problem. We have found that the merry-go-round with the child on it will have an angular acceleration of 3.33 radians per second squared. Before we go on to part C, I want to go on a side tangent and consider a different scenario. Let's suppose that the parent is pushing on the merry-go-round with a force of 250 newtons, just like before. But let's consider that maybe the parent's in-laws come along and decide they don't like it, that's too fast. So they're going to push in a direction something like this on the merry-go-round. And we'll say they push with a force of 150 newtons. So the force from the push of the in-laws is 150 newtons. Now, from looking at this scenario, the way it is drawn, I could infer that the push from the parent will try to make the merry-go-round spin in a counterclockwise direction, but the push from the in-laws will try to make the merry-go-round spin in a clockwise direction. So they are essentially pushing against each other. Now, because the push from the parent is stronger than the push from the in-law, I do expect that overall the merry-go-round should be spinning in a counterclockwise direction. The merry-go-round must spin clockwise or counterclockwise. It can't be both. And because this is the stronger push, this is the one that will win out in the end. How should I treat this scenario where we have more than one force causing more than one torque on an object? Well, let's first calculate the torque from the in-laws. We already calculated the torque from the parent back in part A. So we'll assume that the in-laws are optimizing their torque, so they're going to push on the outer edge of the merry-go-round, a distance 1 meter from the center of rotation. So we could say the torque from the in-laws is going to be Rf sine theta, the R is going to be 1, the force is 150 newtons, and we'll assume that the in-laws are also pushing in a direction perpendicular to the line connecting the center of rotation and the location where the force is applied, just to make life simple. So again, we have sine of 90 degrees. So I run these numbers through and I find the torque from the in-laws is 150 Newton meters. So how would I determine the angular acceleration of the merry-go-round with the child on it in this scenario where we have two torques? Well, this scenario is the rotational analog to a scenario where let's consider there is a shopping cart and my dog is in the shopping cart, and then I am pushing on the shopping cart with a force of 250 newtons. And we know in this picture, the shopping cart will accelerate to the right. So here's the acceleration of the shopping cart. But then suppose a Wegmans employee comes along and decides they don't like that, so they push in an opposite direction with a force of 150 newtons. Well, in this case, the force from the Wegmans employee is partially canceling my force, but overall my force is stronger, so overall the dog and the shopping cart together will accelerate to the right. Now let's consider the scenario where instead of a Wegmans employee, I have my buddy also pushing on the shopping cart, giving my dog a very fun ride. If I'm pushing with a force of 250 newtons and my buddy is pushing with a force of 150 newtons, combined, we are pushing with a net force of 400 newtons, and the resultant acceleration of the dog in the shopping cart is going to be even greater, giving the dog an even more fun ride. We have essentially the exact same scenario here. Because the parent's force will try to cause the merry-go-round to spin in a counterclockwise manner, and the in-law's force will try to cause the merry-go-round to spin in a clockwise manner. They are opposing each other. I would say tau net is equal to I alpha, and then when I calculate tau net, I would say 250 minus 150 equals I alpha. Because these torques are trying to get the merry-go-round to spin in different directions, I'm going to take the difference between the torques. Hypothetically, if instead you had an awesome in-law that decided to try to make the merry-go-round spin faster and faster, let's say again the force is 150 newtons, then both the parent's force and the in-law's force will be adding to each other. They'll be helping each other out. And in that case, I would say the net torque is going to be added together. 250 plus 150 Newton meters gives me a total torque of 400. Part C of this problem, we are told that the parent is going to push on the merry-go-round for 0.4 seconds and then presumably let go after that. And we're asked to find the speed of the kid once the parent lets go. The linear quantity speed is related to the rotational quantity angular velocity by V equals R omega. In this equation, R is the distance of the object from the center of rotation. R is not necessarily always going to be the radius of the object. In this particular case, the kid is on the outer edge of the merry-go-round. So in this particular case, R will be the same as the radius of the merry-go-round. But if the kid were halfway between the center and the edge, then the distance from the kid to the center of the merry-go-round would be 0.5 meters. And when I use this equation to find the speed of the kid, I would need to plug in 0.5 meters when I do my calculation. So we know the distance of the kid from the center of rotation is 1 meter. If we find the angular velocity of the kid the moment the parent lets go, then we will be able to solve for the speed of the kid. So what is the angular velocity of the kid? To make this problem simple, let's assume that the parent is always pushing in a direction perpendicular to the line connecting the location of the force and the center of rotation. So the merry-go-round will spin by some amount, and the parent will be pushing in this direction, and the parent will be pushing in this direction, always perpendicular to this line. This is always a 90-degree angle, and then the parent lets go. So what is omega final? Well, if the merry-go-round is initially at rest, the kid saw the merry-go-round, got really excited, ran onto it, and then waited for a push, we would say, well, initially not moving. Omega initial is 0. We also know the amount of time that the parent pushes for, that is t equals 0.4 seconds. And we know the angular acceleration of the merry-go-round while the parent is pushing. So I could say omega final equals omega initial plus alpha t, and I could say omega final is equal to 0 plus 3.33 times 0.4 seconds. And when I put this in a calculator, I find that after the parent lets go, the merry-go-round with the kid on it has an angular velocity of 1.33 radians per second. So now that I know the final angular velocity, I could determine the speed of the kid. The speed of the kid, as given up here, is the distance of the kid from the center of rotation, which is 1 meter. The kid is on the very edge of the merry-go-round. And the angular velocity of the kid is 1.33 radians per second. And when I multiply 1 times 1.33, I get the speed of the kid as 1.33 meters per second.